Okay, so yeah, Manjula, welcome back. So now we are going to start uh, from where just exactly we have left yesterday. So it's good that it is better now, Manjula. So now yesterday we have tried to understand a very important concept of sampling distribution, wherein we have come to know that how statistics actually helps us in understanding the concepts a little better, and how on earth does statistics come into picture when actually we are trying to do research. So today I will take the story little ahead from there, but before that, to make a background, I would like to discuss with all of you something which is called as sample, something which is called as sampling, and something which is called as sample size. So these three things are important, and important to understand in the sense that we need to know difference between all these three. All right. So let me just try to throw some light onto these individual subjects. Now the first one is sample. Now, sample is something, the people that we select in order to carry out our work, and these people selected actually helps us in collecting the data, and then we analyze the data, and then we say that this is my result. So that is something which is called a sample. Now when we come on to sampling, sampling is an important word in the sense that sampling is the process by which we select the sample. All right. So meaning thereby, if you have heard about sampling, then you would also have heard about something which is probabilistic sampling, something which is non-probabilistic sampling. So whatever sampling method we encountered to, the whole agenda of sampling as a concept is to have a representative sample. All right. When we talk of sample size, now sample size would only tell us that how much or how large should our sample be. Now sampling, essentially, now suppose sample size as a concept tells us that we need to interview about 400 people. Now this 400 people has to be selected in such a way that they represents, all right, that they represents the entire population that we are trying to work on. Now I do not want you to confuse onto these two concepts, because just reiterating it again, that sample size just tells us that 400 size of sample would be enough to cover the maximum amount of variation in this population. But that would not mean that you go to a one place out of that population. Just to give you example in specific, now suppose I want to do some study in Delhi. All right. So after doing a pilot study and after doing statistical calculations, I came to know that to conduct a study in Delhi, I would be requiring a sample size of say 1000 people. So this 1000 people, it would not make any sense if I go to a single place in Delhi, suppose South X. I go to South X, South X would have obviously more than 1000 people. So if I get the data filtered from 1000 people of South X only, then absolutely that will not represent Delhi, right? So when sample size says that 1000 would be enough, then it means that the 1000 people has to be selected so that they're representative of entire Delhi. Now this is an important thing. So how do we come to know that we have actually selected a representative sample? We can never be sure of, but we can only minimize our error. All right, and that is something that we do with the help of sampling. So sampling would talk of probabilistic sampling. So probabilistic sampling is the method of selecting these 1000 people from Delhi so that every individual who is living in Delhi has an equal chance of getting selected in the sample. So which means if I go say by a method of sampling which is probability sampling, say random sampling method, say systematic sampling method, they both are probability sampling methods, then I would say that if I actually follow these probabilistic sampling methods, then I happen to choose one individual from South X, another individual say from Green Park, another individual say from Najafgarh, another individual say from India Gate, so that entire Delhi can be represented. So we need not to confuse between those two concepts, that sample size is 1000, but that is not going to tell us that from where should I select it. So this 1000, it will just tell us that are enough if you want to cover up this variation in this population, but this 1000 people have to be selected following a certain method so that it can be approached to the maximum representation of the population. So that is something that sampling helps us. Sampling says that every individual should have an equal chance of getting selected if it is a random sampling. So that we will apply after having the size of sample decided to you. Now this was the background that we were talking about. So with this background, we will now start to understand the question which we have left unanswered yesterday. And the question was that how do we actually statistically decide onto the size of sample? So if I can go back to the PPT that we were looking yesterday, and if I can come on to last slide of which was talking of normal distribution. So I just want to rerun very quickly through what we have discussed yesterday. The normal distribution, when we were talking about, now it is a probabilistic distribution which is also called continuous distribution. Now it has some properties, and those properties were that it will be bell-shaped curve. It can be, if you cut it in half exactly from the middle of it, then exactly half portion will be left onto left hand side, half portion will be left onto right hand side. So it is equally divided. The middle portion of it is the bulkiest one, and that portion is mean and median and mode. Why it is mean and median and mode? Because in normal distribution we have mean equal to median, median equal to modes, which means all the measures of central tendency would be equal when we are talking of normal distribution. All right. Now we will be talking a little bit of maths today, when we will try to understand how to approach to a approximate sample size that will cover maximum amount of variation. So that maths may sound a little bit something which is complex to you, but it will be good that if we can lend our minds and understand it. Now starting from here, now you're looking something which is like 0 here. All right, you're looking something which is 1 here, you're looking something which is 2 here. Now let me tell you one more important thing about it, that this is actually something which we call as Z. All right, now this is Z, we call it as Z statistic. Now what is the Z statistic, that I will try to explain, but we have to understand that this is not my actual observation. This is only a statistic which is called as Z. All right, now we can always convert a Z into original statistic. All right, now let me try to explain how does it make all sense. Now it goes like this. Now we were riding onto the concept of sampling distribution. We said that sampling distribution is always a normal distribution, and hence all the properties of normal distribution can be applied to sampling distribution. All right, so we know that in normal distribution the middle part of it would be mean of the observations out of which this distribution is drawn. All right, now I'm just getting you a little back, and we have checked something yesterday. If you all can remember, we said that in sampling distribution, the mean of means, if I can take you back to this slide. Now I'm talking of this thing specifically. I'll just try to highlight it, this portion of it. Now this part, right, this part of it, that mean of all these things will actually be the mean height of the class. So class here was my population. All right, so if class was my population, now that means that in this normal distribution, sampling distribution, uh, the mean of this sampling distribution is mean height of our class. That means mean of this sample distribution is actually the mean of my population that I was trying to arrive at. We have to understand it very carefully. Now properties of normal distribution says that central part of it would be mean. All right, so where we are approaching at, try to understand it. What we are approaching at here is that mean of population, all right, is actually equal to my mean of normal distribution. So that means that whatever observations that I have in middle of this normal distribution, all right, their mean, so these observations are equal to mean only, mean of the population only. So if I am to put it in simple words, then suppose out of 58 students, I happen to pick up one student whose height is 172 centimeters. All right, and suppose the mean height of the entire class is also 172 centimeters. So this guy whose height is 172 centimeters actually comes in the middle portion of this normal distribution. So the only thing which I am trying to convey here is that at middle part of it, the mean of population and the observation that we are talking about are equal. All right, so does it make sense? I just would like to understand, is it making some sense, or have you understood this concept? Okay, Rajat, thank you. Now just I have to open Excel again. All right, now we will just try to understand what that z was. Now you have looked at the x-axis, wherein I have talked about 0, I have talked about 1, I have talked about 2, I have talked about 3 and all, and we have discussed it yesterday then that when z is equal to 1, then it means, or within that region, almost 68 point something percentage of observations lie within that region. All right, now that is something which we have done in the properties of normal distribution yesterday. Now let us try to understand this z statistic that we were talking about. Now this z, what is it z equal to? I am talking, all right, that will be equal to x. X is what? X is mean of, or you may call it as observation here, right? X is observation minus capital X, let's call it, and capital X, let it be mean of population, right? So that is how we try to define z. Now if I can close it into parenthesis entire thing and divide it by something which is standard deviation, right? So standard deviation is something that we were trying to discuss yesterday. So standard deviation, if I have to rerun through it very quickly, it would be the mean deviation of all the observations from the mean of population. That is how we tend to define standard deviation. Standard deviation is actually a check of variability that data has in itself. So a value of standard deviation would tell us whether data is highly distributed or it is very minutely distributed, or how much of the data is actually very near to the mean, or how much data is distributed and is away from the mean. So these all properties are actually told to us by standard deviation. Higher the standard deviation, higher the variability into the data. So that is something that we are trying to approach it as. Now if you look at the above part of it, just try to understand. Now this part of it, which is observation minus mean of population. All right, now recall that normal curve and the middle part of it, wherein we said that the observation, now the example which you took was 172 centimeter height of the candidate, and if 172 meter happens to be the mean height of the class, all right, so which means that the point where both these means coincide, understand it, the point where both the means, which is observation and mean of the population, coincide, at that point z will be 0. How come? Because x here is also 172 and this x mean of the population is also 172, and they are equal at middle point of it, and that is the reason, that you see z as 0 here. All right, because when we subtract x, which is observation, minus mean of the population, which is also equal in case of normal distribution in the middle part of it, then you will always have z as 0. All right, so similarly we will have z as 1, z as 2, z as 3. Now suppose my standard deviation, here is 5 centimeters. All right, suppose my standard deviation is 5 centimeters. That would mean that on an average, if mean height of the entire class is 172 centimeters, on an average the spread of the height of the class is 172 plus 5, which is 177, and 172 minus 5, which is 167. So the range in which most of the class height lies is 167 to 172. So this is maximum part of it and this is minimum part of it. That is when we have subtracted, if mean height was 172. All right, so I know the standard deviation is 5 centimeter. All right, so what essentially I have done is from 172 I have subtracted 5, and hence I am coming on to a figure of 167. I have added 5 centimeter 172. So you just understand it that this is only for one standard deviation, right? This is for one standard deviation. So that would mean if I can go back to this curve, so in this region, in this region, which is actually between 1 and -1, right? So here the mean height of the class, which is that -1 would represent 167 and 1 would represent 177. So this range of height, try to understand this range of height which we have now arrived at between 167 centimeter to 172 centimeter would have 68%, or that will be height of almost 68% of students of the class. Now that is how we try to apply normal distribution into general practice. So if I talk of z as 2, z as 2 would mean what here? Go back and we will realize what is z as 2. Now z as 2 would mean 10 centimeter. So a z value of 2 would mean 2 multiplied by 5, because 5 is my standard deviation and that is 10. So a value of z2 would mean 10. So 10 would mean what? So 172 was my mean. So when I am trying to check the mean value at z equal to 2, then it would mean the maximum value would now become 182 and minimum value would now become 162. So now this becomes the range. So if I say that the number of students or the percentage of students in this class of 58 students whose height is between 162 centimeter to 182 centimeter are 95% for 5, because we do understand and we have discussed it that for a value of z2, 2 minus 2, the number of observation would be 95.45%. So almost 95% of the students in this class would have a height between 162 centimeter and 182 centimeter. So that is how we apply and understand Z, and we apply it onto the normal distribution. So does it make sense now? Just want to understand, does it make sense till this point? Okay, so Rajat and Manjula both understood, and Vijendra, I hope you would have also understood it. So now just going back, Vijendra also said yes. Now let's just go back. So now I will take this formula of Z only. So just one more beautiful thing I want to discuss with you guys, and that is that now understand the genesis of Z here, which is 1, which is 2, which is 3, or which is 4. Now what happens is, now this is 1, this is 2, this is 3. When we say, can I say it like this? Now let's interpret Z in some way. When Z is 1, alright, when Z is 2, when Z is 3, whatever is the value of my observation at Z equal to 1, which is 172 plus 5, 177, right? So here value is 177. At Z equal to 2, value is 182, right? So I'm trying to write it down 182. All right. So similarly, we will have a value of x for 3. So what essentially I'm trying to understand here is Z is nothing but is a measure of how many standard deviations and observation is away from the mean. All right. That is just I'm trying to understand, because at Z equal to 1, I am almost 5 centimeters away from a mean height which was 172, right? So now I am 5 centimeters away when Z is equal to 1, but when Z equal to 2, then I am about 10 centimeters away from the mean value, which is 172, right? So Z is nothing but actually is a measure of how many standard deviations away we are from the mean. So one standard deviation is equal to 5 centimeter here. So 2 standard deviation would become 10, 3 standard deviation would become 5 multiplied by 3, 15. Alright, so that is how we try to understand Z here. And Z, look at the formula now. Now that would become observation, all right, minus mean of population, which is my real mean, divided by standard deviation. All right. Now let me write onto this formula Z, which is equal to this. Now have you understood this thing, that the Z actually is something which can be taken as, so Rajat has a question here. Basically we are calculating the spread or percentage people who are 5 centimeters away from the mean, then the percentage of the people who are 10 centimeters away from the mean, and so on. Absolutely yes. And that is what essentially normal distribution helps us in understanding. So we have a range. Now suppose we have a range between 162 to 182. So how many people are in this range? We would say they are 95%, because we know that when Z is minus 2 and 2, the number of observations that are in between this range of Z are almost 95%. So when we are talking, when Z is 1 and minus 1, the number of observations which are within these two categories are almost 68%. So that is something that we are trying to arrive at, and that is the beauty of normal distribution, and that is how it helps us. So the standard deviation is a value we choose. It's like a unit, right? No, Rajat. To choose standard deviation, statistics has a different take on it. Uh, I will tell you book Vijendra also. Now, what is this? When the question asked by Rajat says that standard deviation is a value that we choose, so we will say that it is not that we choose. All right, and I will tell you why do we not do it. Because let us try to understand why it so happens, and let us first try to arrive at how do we calculate the size of sample. Now, Z equal to observation minus mean of population, standard deviation. Now I just want to ask a simple question from you. Now suppose that mean height of your class is 172 centimeters, right? Mean height of your class is 172 centimeters. Now that is your mean of population. That is something that you are trying to arrive at. Now, suppose you are trying to carry out a project where you say, or you are yourself also trying to measure height of a bundle of people, and you say that the maximum error that I allowed, understand this point, this is very important to understand sample size determination. Now, suppose you say that at the max, I will allow an error of 3 centimeter while I am generalizing, or while I am predicting by picking up a sample, that this is mean height of the class. If I have to put it in other words, suppose this is the class of 58 students, suppose I have picked up sample of 5 people, and now on the basis of the data which I have these 5 people, I want to predict, and I will take an average of these 5 people and will say that this is the mean height of the class. Whatever the mean height comes out to be, if whatever that result is, if I only allow error of 3 centimeters into it, all right, so are you understanding it? I want to have your opinion. Suppose I only want 3 centimeters of the difference of, or the error, to be incurred in my result. So which means if I am getting 187 centimeter as a result out of my sample, now that is something that I will not accept it. Or eventually I should not get a result which is 187 centimeter when real mean height is 172. Essentially what I am trying to put is that I will only allow for the sample to be that large so that it cover that kind of variation, so that the result which I will get out of this sample would be between 175 and 169, which is 3 centimeters away from the real mean. All right, so can I call this difference as uh, as representative of x observation minus x, which is mean of population? So can I represent this thing by d, which maybe you take it as the error or the difference which is allowed between the real mean and the mean that you are going to get out of your sample. All right, then let us divide it by SD. SD I have represented as standard deviation, and that is your Z. All right, so now we are sitting at this formula, that yellow one. So Z is equal to D divided by standard deviation. Now D is nothing but is the difference between your observation and your mean of population. So observation here is what? Observation here is the mean of the sample that you selected. So you want the difference between the mean of the sample that you will select or mean of these 5 people that you've selected as a sample, and the real population mean, which is real mean height of the class, to be D, and let's call D as 3 centimeter, let's call D as 5 centimeter, let's call D as 1 centimeter, that is on to U. Alright, so that is something that we are arriving at. So does it make sense till this point? Okay, now let's bring in some more maths in between now. Now if this is D, now I'm taking standard deviation as a different thing. I'm just picking it here. So standard deviation we have been discussing since yesterday is nothing but the deviation of the observations from the mean and a sum of it, or in other words I would say standard deviation is the sum of the deviations of observations from the mean. So what do I mean by that? Suppose I have this 1 2 3 4 5 and 6. All right, now suppose what is mean of this? Let's calculate mean. Now mean would be, sorry, I am trying to calculate average here. So the formula is average. This is the thing that I'm trying to calculate. So I will get average of this thing. So it comes out to be 3.5. All right. Now this is my mean. What is standard deviation? So standard deviation of this is 1.87. So that means that almost 68% of these observations are lying between, you add 1.8 into 3.5 and you add 1.8 from 3.5. So that is the explanation from the point of view of normal distribution. But what is this 1.87? That is what we are trying to understand. That is SD, which is this thing, which is 1.87 for this data. So what is this 1.87? That is what we are trying to understand. Now this 1.87 is nothing but it actually, our mean is 3.5, so I would say 3.5 minus 1. All right, so let's call it 2.5, and no, why to call it, this is 2.5, so let's call it x1, right? So this is x1. So similarly we can have x2, that would be 3.5 minus second observation. All right, then let's take x3, which is 3.5 minus this thing. All right, so we will keep on having these entries. So in all we will have 6 entries because we have 6 observations, right? So if all these 6 observations can be added, now if I add on, all right, if I take a sum of these observations, I would have had 6 observations here. So if I would have calculated all the 6 observations, I would have taken sum of it, and if this sum would have been divided by the number of observations, which is 6, so 4.5 divided by 6, so that would have been my standard deviation. Are you getting it? Does it make sense? So if I can do it so that you people can understand it well, so x4, let's take it as x5, let's take it as x6. All right, so x4 would become how much? So this minus 4th, and this would become this, and here this equal to this minus 5, and x6 would become equal to 3.5 minus 6. All right, so this is how you take it out to be. Now this is coming out to be 0. Now that is what I was actually trying to explain to you, and this is one of the most significant problems that you arrive at when you are trying to calculate the deviations of the observations from the mean. This is a very important property, you always remember it. Whenever you are going to take sum of deviations of all the observations from the mean, that sum is always coming out to be 0, and that is essentially the measure of variation. So to avoid this property, what statistician does, they said square this thing, so that would mean this multiplied by this again. So this is how you are. So you will have a square of 1.5, you will have a square of 0.5, square of this, square of this, square of this, and now this square is to be added. All right, and that is to be divided by number of observations 6. So I'm telling you the statistical formula of calculating the standard deviation. The entire idea of taking you all through this exercise was just to let you know that standard deviation actually considers all the observations, how far they are from the mean. That is why we have taken this thing as, if I can tell you which observations are considered, you see this blue thing which is 3.5, you see this green thing which is 1. So when calculating standard deviation, we are considering mean and we are subtracting the mean and observations, or essentially what we are doing in the process is we are trying to understand that how observations, which is 1 here, is away from mean, which is 3.5. So we have subtracted and hence we are getting the deviation from the mean, and that is the entire idea of standard deviation, which actually tells us that how far away are the observations from the mean value. That is our standard deviation. But when we try to do it, we know that this sum would always be 0. In fact, this is a theorem in statistics. So to get rid of this problem, we will square these results, all right, and square it and then divide by n, which is number of observations, all right. So that is how we tend to do it. So the formula for standard deviation that we were trying to understand here was standard deviation, all right. So the difference, that is something which we have done here, 3.1 minus 1, square of this difference, all right. In the square of this difference, I would say s cubed, square of this difference, because we know that if you do not square, then sum will always be 0, all right, and then divided by n. This will be the standard deviation. This is how we try to calculate it, all right. Now then the problem arises, and problem is that if I am taking square of these deviations, then square of 2 becomes 4, square of 9 becomes 81, square of 11 becomes 121. So it is exemplifying the results. So then, to bring it down to the real units in which the observations were taken, we take square root of it, all right. So that means square root, if I can write it like this, of this thing, all right, of this thing, and then we will do it. If I call this thing as small x, then I take square root of x, right. So this is my actual standard deviation. That is how standard deviation is calculated, all right. Now this value of standard deviation, if we can put across here, then we can actually come to know how do we then we can actually come to know what will be the size of the sample. But there is one problem here. What is the problem? Can you recall yesterday when we were trying to understand normal distribution, we have discussed two very important things, and those things are that mean of all the means of the samples that could possibly be taken out of a population of finite size would always be mean of the population, all right. But the same is not true if we are talking about standard deviation, right? I hope you all can remember it, right? So yes, Rajat, 68% is standard one. It's the constant. When z is equal to 1, 68%, 68 is constant if data is distributed normally, all right, if it is following normal distribution. So when we are trying to understand that mean of the means in case of sampling distribution will always be mean of the population, but same is not true in case of standard deviation. That is something that we have discussed yesterday. So yes, Rajat, same is true for Z2, same is true for Z3 also. So which means if you are talking of value of Z as 2, then we would say that if it is a normal distribution, in case of Z2, the number of observations that would be actually arriving within this periphery would be 95%, right? So this is something that we are trying to understand. Now, I was talking about that standard deviation of sampling distribution actually is not standard deviation of population. So there is a relationship between standard deviation of population and standard deviation of sampling distribution. So when you are calculating standard deviation of sampling distribution, then you have to understand it, then you have to take square root of n instead of n. Now this is the relationship that has been proven. So that is something that we will put across here. So let's keep D as it is, divided by, now instead of this standard deviation, I will put across a formula of it. Alright, standard deviation formula that we all are aware of, this is square root of D and under root of n. So we will have divided by under root of n, that is something that we can square root of n, that is something that we can arrive at. Alright, so n would come in the denominator. So if I can take n down there, then actually I can have this thing. So if I can take square root of n to this side, then d would actually be divided by z. Alright, so this is how we try to calculate z here, right? So there is one more thing that arrives, that is standard deviation, which is an important part of it, right? So here b, which is kind of a difference between observation and mean of population, right? So we have divided it by standard deviation. So standard deviation, the thing that we were trying to discuss, would actually be equal to this square root of n would actually be equal to standard this standard deviation of sampling distribution. Now do not confuse it by this, because it is little confusing. The standard deviation, this standard deviation is of sampling distribution, right? Now standard deviation of sampling distribution that we are trying to do here is equal to standard deviation of population divided by square root of n, which is your sample size. This is the relationship that we are trying to do. Now when this is the case, let us put this thing. So now we will be confused, so I am deleting it up. So now put this thing in this formula. So we will keep d as it is, this is this d, divided by this SD is sampling distribution, because we are talking about sampling distribution. So we will put this thing here, divided by SD. Alright, fine. And then if this is in denominator of it, then it essentially will come in numerator, and hence I can multiply it with square root of n, right? Square root of n, and that is your z. Does it make sense? Right? So which means that if I have to take, can I do it like this? So z multiplied by sd and divided by d, and that is your square root of n, right? So square root of n is this. So if I have to take the real value of n, which is my sample size, then I will need to square both the sides. So when I square both the sides, then I will do square of z multiplied by square of sd, right? And that is divided by d, square of d, square of d, right? So that essentially would be your sample size. So that would be equal to n. So you put these values and then we will arrive at the size of sample. So let us see what are these z, let us see what are these sd, let us see what are these d. So square root of z, what is z? Now as Rajat has asked, now look at this thing now here. Now z will be either 1, either 2, either 3 or either 4, because a value of z would determine that how many observations are you going to select. So in normal case, what we do is we tend to accept a confidence level of 95%. Now what is this confidence level? Just to give you a brief overview of it, confidence level would mean that how many observations that actually you want to be accepted when you are getting a result out of your sample thing. So if we take 95% of confidence level, then value of z is near to 2, right? So you can see this thing, when I'm talking of value of z as 2, this side and that side, then these are the observations that I'm talking about, which are roughly 95.45%. So if I exactly say, right, if I exactly say what about exactly 95% of population, so in that case z is equal to 1.96, right? So this is the standard value of z when we are thinking of accepting 95% of the observations that are here. So at 95% level, z is 1.96, right? So at 95.45, which is the case here, z is exactly equal to 2. So now this thing when we know, right? So there we can put the value of z as 1.96 if you are taking 95% of confidence interval, and if you are taking exact value of z as 2, then the observations that you're talking about would be 95.45. So here you can put value of z as 1.96. Now this is square root of standard deviation. Now this standard deviation is of population, right? And this is square root of d was what? If we can go up, we can actually come to know what amount of error will I maximum be allowing in my result. So if I say that I want maximum of 3 centimeters error by trying to calculate this size, so I would say that 3 is the error that I will be allowing. So this d would be 3 here. Now the thing which is left, which is not available to us, is standard deviation of population. It is not very much easier to get standard deviation of population. So in statistics, what do we tend to do is we tend to actually approximate, the standard deviation of population by standard deviation of sample. This is an important thing to understand. All right. So when we do not have standard deviation of population, which is required here, we approximate this standard deviation with the standard deviation of our sample. All right. So what do we essentially do? So this is the formula of calculating n, which is my sample size, and that will actually tell me that how much sample size should I be taking out. Now you see how important this formula is in the sense that it is considering standard deviation. So you see d, which is the difference, which is the error that you are allowing in your result, that is in denominator, and z and standard deviation are in numerator. So greater the standard deviation, higher will be the sample size. So more variability into the data, more will be the sample size required to cover it. So greater the z, greater will be the n, and higher the precision. This d is also called precision. Now what do I mean by higher the precision? Higher the precision would mean that nearer the result you want to the real mean, which is this thing. So if you want to get to this near, if you say I will only allow 3 centimeters error, so you would perhaps be sitting here. So you are getting more precise to the results. So when you are trying to be more precise, when you want this difference between observation and mean of population to be less, all right, or to be less, then in that case when d is less, then n will increase, because n is inversely proportional to this d, which is difference between the mean of observation, the mean of sample that you will be taking, and the real mean. So just reiterating the facts, that greater the standard deviation, which means greater the variability, higher will be the n, which means you would require more number of people. Greater the precision that you want, more will be the number of people, because greater the precision, lesser will be the value of d, and when anything decreases denominator, numerator is tend to show an increasing trend. So this is how we tend to do n. Now the thing which is left is how to arrive at standard deviation of population. We simply take standard deviation of sample that we have selected as standard deviation of population. Now some genuine questions would arrive here. These questions would be that how do we know? Now we have said that standard deviation of population is approximated by standard deviation of sample, but this whole exercise is being done only to arrive at sample size. So what to talk of how do we take standard deviation of sample? So how do we arrive at the sample size is, generally what happens is, understand it carefully. This is how this all starts. Now suppose I have a project where I have to work on that how do I decide on to the size of sample. So what do I do? There is a term which is popularly used in research, and that is known as pilot study. All right. Now pilot study is a word which is given to a raw kind of study that we do prior to our main study. So in this pilot study, you can on your convenience select any number of people, say 100 you select, 100 is desired, all right, but these 100 people again are to be selected on the basis of a sampling process, which may be a probabilistic sampling, which may be any other method of sampling. So which means if I'm doing it in Delhi, I would pick up say 100 people. I would pick up these 100 people by following the sampling procedure, so that these 100 people, to the best of my knowledge, are representative of the Delhi region, right? And then out of these 100 people, I will have the data filled up to me, and from that data, I can actually come to know what is standard deviation among these 100 people. So the standard deviation here that we are talking about is actually approximated from the standard deviation of pilot study that we do. And that pilot study, one of the major objectives of pilot study to be done is so that we can know roughly what is the variability in our data. So having known this variability, then we can actually arrive at n, that what should be the actual size of our sample when we actually conduct the study. That would mean having a value of z as 1.96, standard deviation we have arrived at by doing pilot study. Now d is something which is the difference between the figure that you will get as a result of your sample and the real population mean. So this is something that you have to decide how much error do you want. So as a researcher you have to decide it. So having these three things, you will decide the value of n. Alright, so this is how sample size is selected. So just to take an example, now suppose z is 1.96, so that would become equal to 1.96 multiplied by 1.96. So that will always be the case because this is square of z. Now then we multiply it by standard deviation. All right, so suppose the 100 people that I have surveyed in Delhi, now those 100 people have given me a standard deviation of say 10 centimeter when I'm trying to observe mean height of Delhi citizens. Now this is square of standard deviation, so I'll have to do square of it. All right, and then we do, let's make it a parenthesis so that we do not actually overlook the basic operations of mathematics. Now let's divide it by square root of d. D is what I say, I only want, or I will only allow an error of 3 centimeter when I'm trying to calculate the mean height of Delhi citizens. So I would say 3, and this is actually 3 square. So let us do it like this. All right, so in this case, this will be the sample size that I will be arriving at. Alright, now suppose if the variability is like this, so this way we can actually arrive at that how much should be size of our sample. So this actually essentially will tell us that how to arrive at the size of sample when we are trying to do any kind of a study. But when you have a smaller sample, now this is a general thing that I am trying to discuss with you. When you are trying to take a smaller sample, all right, as you take in a pilot study, suppose 100, so the more and larger the sample, better would it be. And this is because of a reason. There is a theorem in statistics which says, and listen it carefully, that as we go on increasing the size of sample, as we go on increasing the size of sample, the distribution of that sample tends to become a normal distribution. So if you are talking of a sample size of say 2000, so the behavior of distribution of these 2000 observations would essentially become normal distribution. So lesser the sample size, more will be the variability, and it may not be normal distribution, but as you go on increasing size of sample, that would become normal distribution. So it is expected that you take a considerable amount when you are trying to do a pilot study. You take 500 if the population is fairly large, you take maybe 400, maybe 300. On the basis of that, you decide what is variation into this of samples that you've taken. But again, reiterating it, that this 500 people that you are taking need not to be from only one area. So you have to follow the sampling procedures, and you try to make it as representative as possible. Then you see what is the variability, and then this variability is put into that formula that we were talking about, and putting it into that formula, we can actually arrive at the size of sample that we are talking about, or we should actually take when we are doing this study. All right, So this is all about deciding size of the sample. So did it make some sense, or it was too mathematical? Okay, Manjula said yes. So, but to get more clarity about it, I think that you need to refer to some text which would actually be very beneficial to recall this concept. Otherwise, it is very easy to forget it. So, to refer to a text, that the question that Vijendra also asked somewhere in between. Uh, Basically, if you have any statistic books available with you, all statistic books actually talks of this concept of normal distribution, this concept of Z. All right, you can refer to any statistic book. But if you want my opinion, then there is a book which is known as Business Statistic by J.K. Sharma. It's Pearson is publisher of that book. So he tried to explain it well, that how do we take Z and how do we arrive at the sample size. All right, there is one more book which is research, but that book actually deals with marketing research as such. So if you would like to have a look at that book, then it will also be beneficial to you. The book name, uh, Vijendra said, please repeat the author name. Author is J.K. Sharma, Professor J.K. Sharma, and book's name is Business Statistics. Pearson is publisher of that book. So that book has tried to explain the concepts in very good form. And then one more thing, when we are trying to select the sample size determination, for that you can refer to a book called Marketing Research, and that book is by Naresh Malhotra, Professor Naresh Malhotra. It's an eminent uh, scholar. He does a lot of work, and he tried to explain the concepts very, in very plain English words, so that it is very easy to understand. So the concept that we have tried to do today, when we are trying to determine the sample size, that all is explained in that book. So you can refer to those texts, you can read them up, so that you can get more clarity about it, because not everything can be shared when we are sitting miles away. Not everything actually can be explained in just 1 hour. So there are lot many things obviously which has to be omitted in constraint of time. So those things actually can be looked at when you go through the text, right? So this is it from me. So if you have any questions, then please let me know. Okay, so no questions from now. So thanks for your uh, time. So